Welcome back to Control System Lectures. In this video, let's walk through several ways to draw and analyze a root locus plot in Matlab, and discuss some of the benefits and drawbacks of each method. Now this video is like the 6th or 7th video in my root locus series, so if you'd like to see the previous videos before watching this one, you can go to my channel and find the root locus playlist there. Now this is not a Matlab tutorial video in terms of how to use the software. It's intended to be a video on how to use Matlab to help you solve your root locus problems. And with Matlab, there are plenty of ways to solve a problem, and so I'm just going to be going through a few of them. Alright, so what is our problem? Well, one of my followers on Twitter sent me this transfer function from his exam, where he was asked to draw the root locus plot. And based on how this transfer function is written with a g of s and an h of s, we can assume that the form of the block diagram is probably something like this, where k is the gain we have control over, g of s is the forward transfer function, and h of s is the feedback transfer function, which are just standard letter nomenclatures. Now I didn't mean to write k before g of s times h of s here. Instead, what I'm trying to show is that g of h can be thought of as everything other than the gain k. Now, the problem doesn't state which part of this remaining transfer function is g of s and which is h of s, but for drawing the root locus it doesn't matter, because if you recall, the closed-loop transfer function for this system is k times g of s divided by 1 plus k times g of s times h of s. And to draw the root locus, we only need the characteristic equation in the form that it's already in, exactly the way the problem provided it. We would need to know g of s by itself if we were concerned with system response and not just the pole locations and the root locus. Okay, so we have our g times h. And now before we do anything in Matlab, we should attempt to draw this transfer function by hand, just to see how close we get. Now first thing I do is plot the locations of the poles and zeros of g of h. And we can see that there are 4 poles at 0, minus 4, minus 2 plus 4j, and minus 2 minus 4j. And since there are no zeros, we'd expect 4 lines to go off to infinity. Let me draw the S-plane and then mark out the 4 open loop poles. And if you watched my other videos, you know to fill in the real axis to the left of the odd critical frequencies. And now we can determine the angle of the 4 asymptotes, which are always 45, 135, 225, and 315 degrees, and that these asymptotes cross the real axis at the center of gravity of the poles and zeros. And that's easy for us to figure out since they are so symmetric, it's just at minus 2. Now we know these lines eventually end up on these asymptotes, but how to get to them either requires some more math or some more experience in drawing root locus. But we do know that the 2 poles on the real axis crash into each other and leave at 90 degrees, and then head towards the other poles where they split off and go to the asymptotes. Perhaps it's something like this dashed line, or perhaps like this solid line. But these 2 different ways to draw the lines aren't actually that different, and we still get the general idea. So with the hand drawing complete, let's go to Matlab and see how to duplicate it there. For this demonstration, I'm using Matlab 2014b, but both slightly older and newer versions of Matlab should work just fine. Now I'm going to build up the root locus slowly at first to show you what it's doing behind the scenes, and then we'll progress through easier ways to visualize it, so please stay with me through it. Now the first thing we want to do is build our transfer function object, and like I've said in past videos, there are many ways to do this. My favorite is just to define a simple transfer function called s, and then I can use that transfer function to build out more complicated functions. And here I'm using s to write out our transfer function gh. Now I've left off the variable k, but I essentially assigned k equals 1, as you can see in the numerator. But by multiplying gh by a gain, we can adjust what k is. For example, if I set k equals 2 and multiply gh by k, you can see that the numerator is now 2. So by multiplying gh by various k's, we can see the impact that the gain has on the system. But before we get to that, a second way to define the transfer function is by using the tf function. Let me bring up what our gh was again as a reminder. Now I define the numerator and denominator polynomial coefficients. The numerator is easy, it's just 1, and the denominator is 1, 8, 36, 80, and 0. Now we can set gh to the transfer function that's built from our numerator and denominator coefficients. And we got the same result. But it did require us to have to multiply out the polynomial so we could get the coefficients in the first place. which is fine if you start with a transfer function in polynomial form at the beginning. Now the last way I want to show you is to create a transfer function using the function zpk, which stands for zeros, poles, and gain. Now you specify where you want your zeros and your poles and what the gain should be, and then it just builds the transfer function. I'll bring up GH again for reference. And we have no zeros, so we pass in an empty matrix. And we have 4 poles, 0, minus 4, and the roots of the second order equation, which are minus 2 plus 4i and minus 2 minus 4i. And again, it is the exact same transfer function. Now I'm going to go back to the representation earlier though, because I like the look of it more. And I want to show you how to find the poles and zeros if you didn't already know where they were. So if you have a transfer function, you can use the function pole to find the poles and 0 to find the zeros. And if we do that, we can find that there are 4 poles and no zeros, just like we solved for before. Or if you're not into simple functions like that, you could also use the function roots, which, as you might have guessed, solves for the roots of a polynomial. You just have to pass in the coefficients of the polynomial exactly like we did for the function tf. And no surprise, we found the exact same 4 poles. But finally, you might not want to solve for the poles and zeros, and instead just want to see them visually plotted in the s-plane. And we can do that with the function pzmap, or the pole zero map. Let me dock this plot so it's easier to see, and increase the line width because they start out so small. And here you can see the 4 poles of the open loop function gh plotted out in the s-plane. And we can use this function to also plot the poles and zeros for the closed loop transfer function. This requires using the function feedback. To show you how to use feedback, let's write a really small script to plot the PZ map for the closed loop system as we sweep the gain from 0 to 10. I'll write a for loop to cycle through the gains. Now I want to use PZ map on the closed loop system for each of those gains. The function feedback will take your feed forward transfer function and your feedback transfer function and create a closed loop system from them. As I explained earlier, we don't know how to split up G and H, so we have no choice but to assume GH is just the forward transfer function, which will multiply by our gain K, and the feedback transfer function is 1, or unity feedback. I'll hold the figure so I can plot multiple times on it without overwriting the previous plot, and then I'll end the for loop. And there it is on the plot. Now it's really hard to see, I should have made the markers larger, but the poles are starting at k equal 1, and as the gain increases, the 2 poles on the real axis are moving in towards each other. And maybe the 2 imaginary poles are coming down? It's too hard to see since we didn't fill in the entire plot. So let's try that again, but this time from k equals 1 to 101, jumping every 10th number. I'll rewrite the exact same script, changing just the for loop part, and rerun it. That's a little better. It's starting to take shape. And it's starting to look exactly like what we drew at the start of the video. But you can see with this method of drawing the root locus, it's really hard to figure out the right range of gains so that the entire plot is filled out. Luckily, there is an easier way to draw the root locus, and that is with the function rlocus. First, let me unhold the figure so we can erase what's already on there next time we plot. And instead of that script I wrote, I can just say rlocus of gh, and like magic, the root locus shows up. And if I zoom in on the area of action, we can see that the locus starts at the 4 open loop poles, and since there are no open loop zeros, they go off to infinity in the manner that we predicted. And that was pretty easy. Plus, we can also add a gain marker to see what value of k it would take to place a root at a certain point. And we do that by clicking on the line where we want to see it. Let me make the font a bit bigger so you can hopefully see it also. And this pop-up tells us some important information like the gain, the pole location, and the damping ratio. And if we grab it, we can drag it along the locus and watch those values change real time. So you can use this to find the gain needed for a certain damping ratio or to see when the system will go unstable. But you can also add more gain markers and move them all individually, which is cool, but the downside of rlocus is that you can't see how all of the roots move at the exact same time. You only have control over one root. Also, you can't easily see the effect of your compensator design on the system. For this, we need to use the CISO tool, which is also called the Control System Designer. To run the CISO tool, you're going to need the Control System toolbox. Now there's a few ways to open up this tool. One way is through the Apps tab. Now my screen capture cut off the top of the screen, but if you click on the Apps tab up at the top, you can see a list of the applications you have installed. And if you have the Control System toolbox, you should be able to find the Control System Designer. Clicking on that brings up the tool and two windows. There's the Design window on the right and the Manager window on the left. And I know this looks daunting at first, but it's easy to get started with it, and then you can explore all of the additional features from there. We'll start with the Manager window and the Architecture tab. You can see a block diagram of the architecture that the System Designer is using, and this matches the one we have for our system. There is a Compensator C, which is just gain K for us. There's the Feed Forward Path G, which is G times H for us, and the Feedback Path H, which is 1. But if you had a system architecture that's different than the one that we're using, you can change it using this Control Architecture tab to any one of the preset diagrams. But we're going to go back to where it was because that's what we had. Now after you choose your architecture, the second step is to assign transfer functions to each block in the diagram. You can do that by clicking on System Data. By default, you can see each one is set to 1, which is a pretty boring system. But we can update it for our system by selecting the forward path G and assigning it our transfer function GH. And once I hit OK, the design window instantly updates to reflect the new system. But by default, as you can see, there are a bunch of plots in the design window that we don't want to look at, so we can customize what we see using the Graphical Tuning tab. So it looks like we have 3 plots turned on, and since I'm only concerned with the open loop root locus, I'm going to set the other 2 plots to none, and they'll go away. We'll get into how this plot differs from our locus in a second, but first I want to show you 2 more ways to open this tool. You can call it directly with the function CISO tool, and again it will default all of the system data to 1s. Or you can pass in the forward transfer function and it will automatically set it for you so you don't need to mess with the system data. It's completely up to you how you want to launch the tool. Okay, so now we can finally check out the root locus plot. You can see the 4 roots in this magenta color, and when you grab one of them and drag it along the locus, all 4 of them move at the exact same time. And once you move it, the new gain of the system is displayed in the lower left. Here it has a value of 116. And as you move the roots, the pole location, damping, and natural frequency are shown real time. So the same information as our locus. But here's where the tool really shines. You can click on Analysis Plots and open a number of plot types and up to 6 different plots. I want to see what the step response looks like for my closed loop system. So in plot 1, I select Step, which opens up a new figure. Now I need to select what the input and output is for my step plot. And my options have letters like R to Y and DU to Y. To figure out exactly what that means, we can go back to the Architecture tab, open up Control Architecture, and this diagram explains all of the different signal names. So for us, we want the step from the input R to the output Y, which is this first plot. And the really cool thing about this analysis plot is that it's updated real time as you move the gain in the root locus. So you can see instantly the effect your compensator changes are having on your system. And you can see what your compensator looks like by clicking on the Compensator Editor tab. At the moment, I just have a gain of about 89, which I can update from here as well and see everything change accordingly. But I can also add poles and zeros to my compensator by right-clicking in the Dynamics area and selecting whatever I want to add. I've added a real pole at -1, and you can see how the root locus and the step response changed because of it. Also, it added the transfer function of the pole to my compensator design. And once I add that pole, I can drag it dynamically in the root locus, or set a new value from the compensator editor. And if I delete it, everything goes back to its original value. But let's add something a bit more complicated, like a notch filter. Again, everything updates real time, but since a notch filter is a little harder to visualize, we can go back to our Analysis Plots tab and add a Bode plot for our compensator design. This will allow us to see the frequency response of our compensator and its effect on the step response of the system at the exact same time. So now if we go back to the compensator editor and we make a few changes of some of the values, you can see the notch width and the depth change in the Bode diagram. That's pretty cool, right? Okay, let me remove that plot and again remove the notch filter from our design so we go back to the way we were at the beginning. And finally, you can also add poles and zeros directly to the root locus using the X's and O's button at the top of the plot. So this is all really cool ways of seeing the relationship between your compensator design, your root locus plot, and the system response for a single transfer function. But let me show you something that is probably my favorite feature of the SISO tool: stacked functions. I'll start by creating a series of different but similar transfer functions. Then I can use the stack function to combine them all into a single object that I'll call GH_stacked. The 1 in the transfer function just means that I want a table that has width of 1, so basically a column of transfer functions. And there you can see we have our transfer function array. Now, you can't see what I'm doing because my screen capture cut off again, but I typed SISO tool and passed it in the new transfer function GH_stacked. I'll bring up and rearrange my windows once again. At this point, it might not look that much different than it was before, but if I zoom in on the root locus, you can see faded dots for all of the poles of all of the different systems. And if I move one of the poles, all of them move. This is because I have multimodal display set. But it gets better, because I can also set that in my step response, either to individual responses where you can see the step response of each transfer function, or to bound, which just shades in the region between the extreme responses. And all of this updates real time. The reason this is so cool is that you can use it to design a single compensator that will work for multiple transfer functions, sort of like a makeshift robust controller. For example, you could add design requirements to the step response plot, like it must have rise time less than 2 seconds and settling time less than 4 seconds with no more than 20% overshoot. Then you can see graphically whether you're meeting your requirements, not just for a single transfer function, but across all of your stacked transfer functions. Here you can see that some of my responses meet the requirement, but not all of them, so I need to work on my compensator. Now the first thought might be to adjust gain only. So I tried that, but as you can see, as I lower the gain, eventually the rise time requirement isn't met on one function before the overshoot is met on the other. So perhaps we can solve this with a lead compensator. Now I have to admit that I'm just trying things based on what I think will work. I'm not putting any mathematical effort into designing this system, so this is not necessarily the best design, just one that might work. Now I can play with the lead compensator a bit, and then adjust the gain until I get something that works. And that's pretty close, I think. You can see that I'm not really meeting my requirements just for a bit, but I think I can get an exception for that. Now I think if you play around with a couple of transfer functions and the SISO tool, you'll gain a better understanding of what the root locus plot looks like for various systems, as well as how adding poles and zeros affect the shape of the plot. Also, you get to see real time the effect your compensator design has on the response of the system. If you have any questions or comments, please leave them below, and I, or hopefully another viewer, will try to answer them. Don't forget to subscribe so you don't miss any future videos. And don't forget to check out the links in the description for more information on these Matlab demos. And thanks for watching.